All right, let's go ahead and get going. We say your instructor today talked about functions of two variables a little bit about graphing them, but said like you're not going to have to graph them. You kind of have to know how to kind of identify some graphs maybe. And then talked about level curves and contour maps. Yes, okay, sure. So let's talk about functions of two variables. And I might get a little bit more involved in the graphing of them because I think that's a worthwhile skill, but being able to identify graphs is certainly useful. So let's take a look at, sure, one of my favorites, which is f of xy equal to 9 minus x squared minus y squared. And so if I was trying to kind of identify what this graph looked like or try to graph it even, I would probably do a couple things. I would probably start by actually looking at what's called the traces. And we might know, let's see, I just want to think about this for a second. Yeah, that's fine. So traces are what you get in each of the different planes. In fact, I think we might take a minute here. We'll come back to this in a second. I kind of got ahead of myself. Let's skip this for a moment. Sorry, I just realized like we should talk about the planes before we talk about the traces. So let's talk about the planes. So graphing planes / talking about planes. So there's some pretty important planes that I think about when I am graphing things. Like the plane z equal to 0. So when we think about this equation, we're literally saying, okay, in three-dimensional space, we want all the points where z is equal to 0, which means x and y can be anything. So what we're literally getting, we graph our three-dimensional coordinate system here, where this is usually x, this is usually y, and this is usually z. X and y can be anything, but z has to be 0. So we're stuck in the xy plane. Right, we haven't gone up or down, but we can go as far left or right or forwards or backwards as we want. And the way I typically describe this is x is the forwards backwards direction, specifically positive x is forwards. Y is the left right direction, right is positive y, left is negative y, and z is the up down direction. Positive is up, negative is down. Often in the classroom, I'll refer to the corner to your left there on the ground as the origin, and then this vertical line here is the positive z-axis. This horizontal line here is the positive x-axis, and that one along the wall there is the positive y-axis. So I'm typically thinking of that as the origin, and we are sitting in the first octant, where all things x, y, and z are positive. Like in 2 dimensions, the first quadrant is where both x and y are positive. Similar kind of thought there. On the other hand, if I wanted to graph, say, x equal to 0, well, then I can't move forwards or backwards, but I have freedom of movement in the up, down, and left, right direction. So essentially, and again, I'm only graphing a part of the plane because I can't graph all of it because it's infinite. But essentially, x equals 0 is like this over here, where we can move left or right as much as we want. We get points like, I don't know, 4 comma, not 4, 0 comma 4 comma 5, for example. And whereas like over here might be the point 3 comma 4 comma 0. And then you might be able to guess where we're going with this last one here. If I was to graph the plane, say y equal to 0, well, then I have freedom of movement in the x and z direction. So I'm on this plane over here. Notably, y equals 0 is equivalent to the xz plane. X equals 0 is equivalent to the yz plane. And z equals 0 is equivalent to the xy plane. There are, of course, other, so these are not the only planes, obviously. There's lots of other planes. We often specifically like to think about planes where z is equal to a different constant, because that's where we're going to how we introduce the idea of level curves. So for example, and again, graphing, it's not really lovely because it just kind of looks like you're drawing lines out in space. But if I wanted to say graph the plane z equal to 4, I would draw my coordinate axis system, and I try to use different colors for my axes and the things I'm drawing because it helps a little bit make it discernible. So if I was going to graph z equal to 4, I would start at the origin. I would go up 4. I'm just making up marks here. And then from there, I have no freedom of movement up or down, but I can move left, right, forward, backwards. So I can go left, right as much as I want. Forward is this slanty x direction here. So I'm going to try and draw this line parallel to my x-axis I've drawn there, like that. So I'm thinking, okay, here's my plane or part of my plane in the, I should say, part of my plane is equal to 4. I'm usually trying to do some sort of shading to kind of indicate, oh yeah, that looks reasonable-ish, right? That whole plane is just the XY plane shifted up 4 units. Anything else I want? Oh, okay. And he talked a little more. So I don't think the other thing he said about planes, which I don't really think you need to know so much, but I guess you might since he talked about it, is I'll say the following. I'll give an example instead of giving the general definition here. So for example, the plane passing through the point 4 comma -2 comma 1 with a normal vector 3, 2, 5. So when you're describing a plane, other than like these kind of basic ones where it's just like z equals something or x equals something or y equals something, the easiest way to describe a plane is by picking a point and then giving a direction of the normal vector. It's kind of like if I was describing a line and said, well, I'm going to give you a point and a slope. That's all the information you need to find the equation of the line. In a similar way, if I give you a point and a direction of the normal vector, that's the easiest way to describe a plane with the least amount of information. Kind of a pain in the butt, not that big a deal. Here's what I really want you to know, and I'll be honest, I think this is interesting. That's part of the reason I'm showing it to you. You'll have to remind me. We learned the dot product last quarter, right? So if I said the dot product of two vectors was equal to 0, you would know that those two vectors were perpendicular to each other, or also known as orthogonal to each other, also known as normal to each other. So those 3 words, orthogonal, perpendicular, normal, for our purposes really just mean the same thing. 90-degree angle. Sometimes there's a little bit more to it than that, but really 90. So here's what we've got. We've got this plane that we're trying to find the equation of. We know there's this point here, 3 comma 2 comma 5. Oh, sorry, 4 comma -2 comma negative comma positive 1. That's the point. And then you've got this normal vector sticking out of it, perpendicular. We usually call that normal vector n. And what's worth knowing here is that this normal vector is perpendicular to any vector that would lie in the plane. So if I wanted to describe a point that's in that plane that I didn't know, like say this point over here, which I'm going to call x comma y comma z. Well, if I draw this vector, let's call it v, the vector v, if you want to find the vector between 2 points, it's the end points minus the beginning points, essentially. So the vector v, the vector coordinates would be x minus 4, y minus -2, and z minus 1. That vector and that vector are perpendicular, which means their dot product has to be 0. So here's how you get the equation. I know he just gave the equation in class, but I felt like I would like to describe it a little more. We're going to take this vector and dot it with that vector, and look what happens. 3 times, let me write it out. And dotted with v is 3, comma 2, comma 5, dotted with x minus 4, comma y plus 2, comma z minus 1. And we literally just multiply the corresponding components together and add it up. So we get 3 times x minus 4 plus 2 times y plus 2 plus 5 times z minus 1. And it's got to equal 0 because they're orthogonal, perpendicular, normal. And that's exactly the equation he gave you in class, right? It was the components of your normal vector multiplied by your variables minus the values of the points that was on the plane went through. Right? He gave this equation more generally. If n is equal to, I forget, I think he said n1, n2, n3, and your point is ABC, then your plane equation was given by n1 times x minus a plus n2 times y minus b plus n3 times z minus c equal to 0. Same idea, literally. But now, at least you kind of know where it's coming from. It's because these two vectors. And so I'll point out, this would be true for any point I picked in the plane. If my point was over here instead, and I call that x, y, z, that vector would still be perpendicular to the normal vector. And so that equation would still hold true for this x, y, z point over here. It's kind of like how we describe all the points on a circle as being the same distance from the center. What do I mean by this? I mean, if you have all the points on a circle and the center is, say, 1, comma 3, and the radius is, say, 4, then any point on that circle is a distance of 4 from the center. So we say, okay, well, let your point be x, comma y. The distance is the square root of x minus 1 squared plus y minus 3 squared. But the distance is actually equal to 4. Sorry, I'm squeezing it in there. That's terrible. And then if you square both sides, you get exactly what we're used to seeing as the equation of a circle. X minus the x coordinate of the center squared plus y minus the y coordinate of the center squared equals the radius squared. And it's true for any point you pick on the circle. So really, when you're writing an equation like this for a graph, what you're really trying to do is you're trying to say, okay, this equation represents all possible solutions that are on the graph. Kind of neat. All right, probably said enough about that. I don't think you actually need to know how to find the equation of a plane based on having a point in the normal vector, but I could be wrong. You might expect that. So I want to talk about it. What else? So then finally, back to where I started. The first page here. Sorry, I kind of took a circuitous route to get here. I want to mention traces. Traces are just what the graph looks like in each of the 3 coordinate planes. So in the xy plane, in the xz plane, and in the yz plane. So this graph in the xy plane, well, in the xy plane, what's true in the xy plane? Which of the 3 things is equal to 0 in the xy plane? Is it x, y, or z? Right, it's always the one that's missing. So in the xy plane, we've got z equal to 0. Remember that your f of xy is also thought of as z. So we're really just saying, okay, great. 0 equals 9 minus x squared minus y squared. Or if you bring those things over there, x squared plus y squared equals 9. So it looks like in the xy plane, I have a circle of radius 3, which I could draw. Looks like that. I mean, it's the circle. Let's look at the other 2 traces. In the xz plane, we're going to let y equal 0. I would say it's pretty standard when you're drawing the traces to draw the XY plane with X as the horizontal and Y as the vertical, like we usually would. For the other two traces, it's almost always typical to draw the Z axis as the vertical axis and either the X or the Y as the horizontal axis. So in the XZ plane where Y equals 0, take this equation here, we're going to set Y equal to 0, and we're going to get Z equal to 9 minus X squared, which is a pretty typical looking parabola, right? It's downward opening, shifted up 9. It looks somewhat like this. And then it feels kind of silly, but we will do it to do the other one. If we look at the YZ plane, we're going to get essentially the same graph. We're going to set X equal to 0. We're going to get Z equal to 9 minus Y squared. It's essentially the same thing. So putting it all together, we essentially what I try to do when I'm graphing a thing like this is I'm trying to put each of these things on their respective planes in a three-dimensional graph and then kind of tie it all together in one three-dimensional surface. So we do this here. I think I can fit this in here. Which I always think I can fit it in there. It always feels like, yeah, there's enough room. So the idea here is that in the XY plane, we have this circle. So it's like that. There's my circle. In the XY plane, lying flat. I always think of the XY plane as one that lies flat on the ground. And then in the YZ plane, we have this parabola like this. Maybe didn't go quite high enough there with my Z-axis. Oh, well. And then in the XZ plane, I also have a parabola, but the XZ plane is always the one that's kind of like cutting out towards you. So it's a little bit tilted. It's not going to look like a flat like parabola. It's going to look like a narrower parabola. So it's going to look like this. And there's our three. Now, I should point out, I haven't drawn all of it, right? This continues down, 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 down the witch's room. So there's our parabola. It kind of looks like a mountain, a very small mountain. What to say about this paraboloid? Good question. Let's talk about the domain for a second. So looking at our original function, do we see any of the usual three domain issues? Are there any roots? Nope. Are there any logarithms? Nope. Are there any fractions or quotients? No. So it doesn't have any domain restrictions. The domain is the set of all points in the xy plane, right? It's not all real numbers. It's the set of x comma y such that x and y are real. The range, on the other hand, is a little more interesting to consider here. The range is the set of all z values, so it actually is an interval notation. The highest z value looks like it's going to be 9, right? You can't get any higher than 9 for z, because if x is 0 and y is 0, z is 9. And if x and y are anything else, the z value, the output value, gets smaller. So our range here is looking like z is less than or equal to 9, aka the interval from negative infinity up to positive 9 inclusive. I do think it is worthwhile to play around with a 3D graphing tool. He recommended one, I forget what it was called. Let's see here. I've got it right here. Except it's so now so the internet's not working for that. Okay, fine. It was math3d.org. I like Desmos 3D. GeoGebra 3D is also good. Whatever you like. It's again, I would play around with it. I would literally show it to you right now, but the site can't be reached. Well, at least the Zoom is still working, so good for us. Interesting that, yeah, like I'm curious here. Okay, maybe it just needed to reload. I don't know. Maybe that one's just terrible. Let me see here. So here's the GeoGebra one that I happen to be a fan of. So you can graph all sorts of things. Usually the easiest way is to graph, well, if it's an explicit 3D graph, like z equal to some stuff like that. So like, for example, we could graph the one we just did, z equal to 9 minus x squared minus y squared. And if we zoom in a little, out, I don't know, one of the directions, you can see, oh yeah, there's your downward opening paraboloid. Or you could use Desmos 3D. That's also a perfectly good graphing tool. And we could graph something else, like we could graph z equal to x squared minus, oops, no, we're good, y squared. Which maybe doesn't look like it super well from here. And I kind of like the translucent surfaces typically, if that's an option. Yeah. What reverse contrast does. Oh, okay. Well, yeah, not surprising. Okay. Exactly what you think it's going to do. But you can turn this around, and this is what's called a saddle, right? It kind of looks like literally the saddle you would put on an animal. Or if you hike, when you like hike over a mountain, you like hike up to the saddle, and then you can either go like over the mountain, or you can turn right or left and go up to a higher peak, also called a saddle, for literally obvious reasons. But then you can also do things like, for example, if, oh, geez, stop moving around. If you want to see what, say, this surface looks like at a certain elevation, okay, well, I'm going to type in the elevation of z equal to 3. And then you can see where these two things intersect each other. And also, if you're smart, you can just hit this button over here that gives you the XY view. And that kind of intersection of the blue and the red, that is where you have the level curve, where you're seeing what this surface is doing at a particular height, particular elevation. Kind of neat. So for example, we can probably do it over here too. Although I feel like this one is less good for like doing multiple graphs. If we plug in like z equal to 2 here, it was z, not c, James. Now, this one might actually be, so you can kind of see, oh yeah, look, that's a circle. They intersect in a circle. Not surprisingly, because if you set 2 equal to 9 minus x squared minus y squared, you're going to get x squared plus y squared equal to some number, which means you have the graph of a circle. Let me pause for a second. So I should just reiterate, in case I hadn't already, your questions are welcome, your comments are welcome, right? If you have thoughts or ideas, you're like, could you please say more about that? Say words, because I'm just like, yeah, sure, this stuff is, I'm like, I know this stuff, it's like super great. But if you want me to say more things about a certain thing, let me know. Happy to do so. Or if you just want me to talk about an example more, I can. Normally I would talk more about like how to graph a saddle or we should talk about a sphere though, or any of these shapes. But again, it doesn't seem like it's going to be a super big deal, so I shouldn't spend too much time on that really. Let me talk about though a little bit more about, where'd you go? There we are. So in order here. The last kind of three-dimensional surface I will mention before we talk about level curves a little bit, which is still involving three-dimensional surfaces, not you, is spheres. And so the equation of a sphere is very, very similar to the equation of a circle. You're literally just adding on another dimension. So circle, the equation very generally is x minus h squared plus y minus k squared equal to r squared. And that's a circle whose center is the point h comma k and whose radius is r. I will point out, because I think it's useful to know, the center is not a point on the circle. Obviously, right? If you look at the circle, the center is not on the perimeter of the circle, which means, as it should, or shouldn't, I guess, the center isn't a point that satisfies the equation of the circle, right? If you have, let's actually pick a specific example, x minus 3 squared plus y plus 1 squared equal to 25, the center is the point 3 comma negative 1. If you plug that point in, you're not going to get equality. You're going to get 0 on the left and 25 on the right. So I always think of the center actually as the point you would plug into the left side of the equation that would make it all equal to 0. That's how I usually think about finding the center. It's the most important point that's not on the graph. in the same sort of way, a sphere, the general equation is, I'm just going to use A, B, and C here, x minus a squared plus y minus b squared plus z minus c squared equal to r squared. And this is centered at the point A, comma B, comma C, with a radius still of r. So one thing I might ask, for example, is what is the center and radius of the following spheres? So here's an easy one. X minus 4 squared plus y plus 3 squared plus z plus 1 squared equal to 36. And you can practically just read the answers off if we've written it this way. The center has coordinates 4, -3, -1. And the radius is the square root of 36, which is 6. Often the radius is a nice integer number. It doesn't have to be, though. The radius could just as easily be the square root of 7, and that's a totally fine value to have for the radius. A slightly more challenging question would be if our circle looked like this. X squared plus y squared plus z squared plus 2x minus 6y plus, let's not make it crazy, James, 10z equal to 14. So first and foremost, the radius is definitely not the square root of 14. And I know that because this left-hand side isn't written in the standard way. So to change this to being written in the standard way, we're going to group our like variables together and then leave ourselves some space to complete the square. So we're going to say that we have x squared plus 2x plus, we'll leave ourselves some space, and then y squared minus 6y and some space, and then z squared plus 10z and some space equals, if we add things on the left, we're also going to add them on the right. So to complete the square, it might have been a minute since you've done it, but you take the coefficient of the thing to the first power, divide that coefficient by 2, and square it. So 2 divided by 2 is 1. Squared is still 1, so we're going to add 1 right there. And we're going to add 1 right there. For -6 divided by 2 is 3, is -3. -3 squared is +9. And then finally over here, 10 divided by 2 is 5. 5 squared is 25. And the reason we've done this is because now we can factor each of these things. X squared plus 2x plus 1 factors as x plus 1 times x plus 1. Y squared minus 6y plus 9 factors as y minus 3 times y minus 3. Z squared plus 10z plus 25 factors as z plus 5 times z plus 5. By the way, this is why it's called completing the square, because you're literally adding the thing on that makes it so you can write it as some quantity squared. On the right-hand side, I just picked a number, so it's probably not, did I happen to pick something? No, I don't think so. 14 plus 1 is 15. I did. I totally guessed a number and it happened to turn out nice. I didn't actually want it to. Oh, well. 15 plus 25 is 40. 40 plus 9 is 49. And so we end up getting a sphere whose center is -1, +3, -5, and whose radius is 7. So I got a handout for all of you. Take one passing around. So here's a somewhat nice-ish visualization of what contour lines or level curves are all about. They're really just on a three-dimensional surface. There are all the points on that surface that happen to be at a specific elevation or height or z value. You can imagine that if you were to be on this mountain and always were to walk on the line 20, that means your elevation would never change, right? You would always be, you wouldn't be going down or up. You would just be staying at the same height the whole time, not ascending or descending. You can see that the contour map, which is the thing down here, is just the projection or essentially the dropping down of all these curves onto the XY plane. Right? Because you can't, I mean, you could, but we don't really like, if you're out hiking in the world, for example, you're not carrying this around with you. You don't have a 3D map that's like just in your pocket. I mean, kind of you do with your phone, but not really, because it's still a 2D projection on your phone, right? Your phone isn't a 3D surface, which is not really a thing I should even say. A 3D object would be the right thing to say. So, right, it's all two-dimensional, and what we're doing is using our brains to interpret one thing into another. So this here kind of shows you what's going on. We can see that, oh yeah, if I just start here and travel this way, I'm going to ascend because I'm crossing those lines that are at different elevations. Whereas if I start here and travel, maybe this way, it's a much longer route to kind of like hiking on switchbacks to ascend this same vertical distance or vertical, I don't know, whatever we'll call it. So the more quickly you cross contour lines, the faster or more steeply you're ascending. The less quickly you cross them, the more gradually you're ascending. And I should say, the closer the lines are together, the steeper the surface is because you're traversing more height over a shorter distance. Yeah, and those ideas are actually important moving forward because we're eventually going to start talking about like derivatives of surfaces and like what it means to have what it means that the derivative is this value. Oh, it means that if you move kind of horizontally in this direction, you're going to expect that much vertical change in that horizontal distance. So this idea of having a change in height as we move in a certain direction is something we will continue with moving forward. So I just want to give you that. I think it's a nicest picture, right? There's lots of so my kind of go-to example of contour lines are topographical maps. That's the one that makes the most sense to me. But there's certainly lots of other examples like heat wave map or like heat maps for areas or wind chill maps or lots of different maps that show like barometer kind of weather patterns in general are pretty often things we see using contour lines because you can't just say it's a certain value everywhere. You have to be like, okay, in this general area, it's about this much. But let's actually get to the drawing of level curves. Yeah, we got time. So it's useful / necessary to be able to kind of what's what I'm looking for? Look at the level curves of the map and be able to kind of think about what the 3D surface would look like and vice versa. It's kind of hard to like draw those examples and be like, here you go. So I'm just going to kind of show you how we draw the level curves and we can kind of work from there. So let's look at two different examples. Let's look at these equations. The first one being, yeah, sure. So I'm trying to think about how I want to do this. Yeah. So they're kind of basic examples that you might have already seen, but they're useful. So we've got z equals x squared plus y squared, which is your usual standard paraboloid. It's kind of like your parabola that has a vertex at the origin that opens upward. It's your paraboloid whose vertex is at the origin and opens upwards. So it's your usual paraboloid like this. Sorry, I have to make sounds when I draw things. It's necessary. Otherwise, I can't draw it well. People often describe the paraboloid as looking like a bowl shape. And it does. I mean, I feel like most bowls are a little bit, not exactly, because some of them are usually flat on the bottom to some degree. Like you don't have a perfect like vertex. That would not be a very good actual bowl. And then we are also going to look at this other shape, z equal to the square root of x squared plus y squared, which is a little bit more interesting. So to graph this, yeah, to graph. So, I'm trying to think about how I would explain it. So honestly, the way I would graph this is by drawing the level curves and seeing what it looks like. So we'll start with this one and we'll draw the level curves to kind of see how they correlate. And then we'll kind of do the opposite thing over here. So the level curves are the two-dimensional curves that we get by setting z equal to values that are in the range. You don't actually have to know the range to do this. If you pick a value that's not in the range, you just won't get any solution. So for example, -2 isn't in the range here, right? X squared plus, if you need me, also, I see your faces looking at like, what did he write? If you need me to clarify something, I'm happy to clarify something. I know my writing is not always or even often excellent. So let's see, this says 2D curves we get by setting z equal to values in the range. And what I was going to point out is that if you think about it, it's not in the range, like -1 here. If you set x squared plus y squared equal to -1, you're not going to get any solutions, right? X squared is always non-negative, y squared is always non-negative. You add them together, it's still non-negative, so there's no solutions. So we wouldn't get a curve there. It'd be an empty set. But if we set like say, and usually for whatever reason, we do this change of letters, which is I find annoying, but it's what people do. So instead of saying z equal to x plus y squared, we're going to say, well, we're going to let z equal k, because k is a constant and z is the variable. And then we're going to say, okay, well, we're going to then say for z equal to k, we're going to have x squared plus y squared equal to k. Now, what kind of two-dimensional curve does this kind of equation typically yield? A circle. With what radius? Square root of k. So, and honestly, that's generally, I would say, you don't want to spend your time picking lots of different values for k. You could, right? Be like, okay, k equals 1. X squared plus y squared equals 1. Radius equals 1. K equals 2. X squared plus y squared equals 2. Radius equals square root of 2. And so on and so on and so on. But that's a waste of your time. You kind of want to generalize here and say, okay, great. For any k, we get a circle. The center is the origin. And the radius is exactly as you said, the square root of k. Now I'm going to cherry pick some k values that make it easier for me to draw this thing. So I'm going to pick k equal to 1 with a radius of 1, k equal to 4 with a radius of 2, k equal to 9 with a radius of 3. I would also say, depending on your drawing skills, it's a good time to use Desmos, really, is actually the answer. But try your best. 1, 2, 3, 1, 2, 3. So here's my, and I usually often try to alternate colors here. Here's my circle of radius 1. My circle of radius 2. Nope, it's a little bit there. My circle of radius 3. Now I'll point out here, usually these come with labels, right? This is my k equal to 9. This one is my k equal to 4. This one is my k equal to 1. So on my surface up here, which you can't quite see, sorry, my k equal to 1 corresponds to having a height of 1. My k equal to 4 corresponds to having a height of 1, 2, 3, 4. And my k equal to 9 is probably kind of off the graph that I've drawn. But literally what you're doing is you're seeing where the plane z equal to 4 intersects the surface z equal to x squared plus y squared. We kind of did that graphically, like, in fact, let me show you just to kind of show you. And we get 10 minutes, we're good. Sorry, if I can show you, maybe. Sure, let's yeah, I'm just not as good with this one. This one's the one I'm better at. So if we were to graph z equal to x squared plus y squared, and then close this for a second, go back to this view here. There's our upward opening standard parabola. And then if we cut it with or intersect it with the z equal to 4, It's too high. That's why. So you're like, why isn't it showing up? Because we're not zoomed out enough, I assume. Maybe am I zooming in? I don't even know which I'm going. There we go. Okay. I was like, which way am I going here? So you can see, oh yeah, their intersection is exactly a circle. And if you want to look extra close, you can see it's a circle of radius 2. It's kind of hard to see the grid marks there, but that end of that circle is exactly where 2 would be. So yeah, circle of radius 2. Great. So now let's use that to kind of inform how we're going to think about the graph of this. So I'm going to pick the same z values for interest. Oh, nope, I'm not. I'm going to be smart and do what I said I should do. I'm going to just set z equal to k and try to be general about it. So we're going to let z equal k. So we're going to get the square root of x squared plus y squared equal to k. Pro tip, if you see an x squared plus y squared, usually you want to isolate that. You want it to be all by itself without anything next to it or as a function of it. So I would square both sides here and say, I have x squared plus y squared equal to k squared. Usually, if you have x squared plus y squared popping up, you've probably got a circle somewhere, somehow. So great, this is a circle, still centered at the origin. But now the radius, instead of being the square root of k, is just k. Which means the level curves. So I'll point out the level curves I've drawn here might be misleading because my k values are not like, what's what I'm looking for? They're not the same increments each time. So like if I were to draw, in fact, let's just do it over here real quick because my drawing is not going to be helpful. So let's do this the smart way. Let's go to regular Desmos. Graphing Desmos, where are you? So let's point out, if we graph these circles, well, not capital X, who just capital X? That's crazy. So there's a radius 1. And so if I increment k by 1 each time, you see that these circles, whoops, sorry. I would say it's kind of hard to see that actually. So let me ask you a question. Are these circles, let me zoom in a little bit actually. Are these circles equally spaced from each other or not? Definitely not, right? And you can see that by the fact that, well, I could have seen that if I had showed it to you by showing that right here, the k value, right? The k value increases by 3 here, the k value increases by 5 here, and the increase in r is the same each time. So to have kind of equally spaced level curves, you'd have to have the same increment corresponding to the same increment on both sides, which is going to be true over here. Because here, if we let's say k equal 1, we're going to get x squared plus y squared equal to 1 squared. If k equals 2, we're going to let x squared plus y squared equal 2 squared. If k equals 3, we're going to get x squared plus y squared equals 3 squared. So here, an increment of 1, the radius also increases by 1. So increasing k by 1 leads to the exact same increase in the radius. So I was going to try and draw the level curves here. How do I want to do this? Sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. I know. 2, 4, 6, 8, 9. So if k was equal to 9, here's my level curve for k equal to 9. We'll pretend like the rest, you can imagine the rest of the circles there. There's my k equals 9. And then my k equals 8 is, just one smaller. There's my k equals 8. There's my k equals 7. So all my level curves are equally spaced out depending on the k value. That's scratch that last comment. It's not really, they're equally spaced out. Full stop. So depending on how, and we were going to graph it. I was like, we were coming back to a graph here. So if the level curves are equally spaced out, here's what our graph is going to look like. It means that every time we go up 1, our radius increases by 1. So try and graph this somewhat nicely. Oh my gosh, it's a miss. Okay. So up 1, radius is 1. So we're about there, looking like that. And then up 2, our radius is 2. So we're looking kind of like that. Up 3, our radius is 3. And again, I'm eyeballing it a little bit here, so it might not come out perfectly. So our radius is kind of following this straight line path. We can kind of draw exactly like that. So here, drawing the level curves kind of shows us what the surface looks like. And instead of being a paraboloid where the circles aren't evenly spaced out, we're getting a cone where the circles are evenly spaced out, however far up we go. It's kind of neat. Yeah. So we have 2 minutes left. Questions, comments, observations, thoughts? Yeah.
Is this leading to like finding the area, like how many with the integral with this?
So I don't actually, I'm trying to remember if there certainly is. I think we did that last quarter actually. So in 17B, we did do double integrals, right? Is it? Sorry, the content, I always forget. Let me look at my notes real quick here. Double integrals is 17C. Apologies. So yes, to answer your question, just like kind of before, we integrated a function to find the area underneath that function. Later on, we're going to do a double integral of a surface to find the volume under that surface. What we're immediately looking at, though, coming up is the concept of partial derivatives, where we'll have functions of x and y. In fact, let me write down, since I have a minute, let me write down one quick example just to kind of help you get ready for what's coming up, because I do think it can be a little bit tricky at first, but afterwards it's super straightforward. So if you had a function of x and y, like x to the 6th plus y to the 5th plus x cubed times y to the 4th, if I wanted to find the partial derivative with respect to x, which means we are pretending like y is a constant, or we're only moving in the x direction, so y is essentially acting like a constant. The partial derivative with respect to x, which we either write as f sub x, or del, which is a curly d, not an actual d, it's like curlier, del f, del x. It's kind of like the difference between the prime notation and the Leibniz notation. We pretend like, well, we don't pretend, we treat x like the variable, we treat y like a constant. So the derivative of x to the 6th is 6x to the 5th. The derivative of y to the 5th, well, y is a constant, y to the 5th is still a constant, and the derivative of a constant is 0. And then for x cubed times y to the 4th, that's a constant multiple. The derivative of x cubed is 3x squared, so we get 3x squared multiplied by this constant that just hangs out. That's very briefly an intro to partial derivatives. On the other side, if we wanted to find the partial with respect to y, which is del f del y, now we treat x like a constant and y like a variable. So the derivative of x to the 6th would be 0. The derivative of y to the 5th would be 5y to the 4th. And the derivative of x cubed times y to the 4th would be x cubed is a constant multiple that hangs out. The derivative of y to the 4th is 4y cubed. So that's very, very broadly how we deal with partial derivatives. Is the variable you're differentiating with respect to, treat it like a variable and treat any other variables as if they were constants. Meaning, if they're on their own, their derivative is 0. If they're multiplied by something else, they just hang out, but they don't change. All right, that's all I got. I'll see you on Friday.